Okay, great. I think we'll make a start now then. So nice to see you back again this morning. And we're going to start off with a session looking at OpenMP performance. So much of this is pretty generic, is not specific to the AMD Rome processors. But I will say something towards some stuff towards the end, which is a little bit more specific. Okay, so I'm in the position of having taught OpenMP for more than 20 years now, and this is a surprisingly common reaction that you get. Okay, so, or at least this is what happens to a lot of people. So so I wrote my OpenMP program. Okay, and I checked it gave the right answers, and then I ran some timing tests, and well, the speed up was a bit disappointing, really. So now what do I do? So if you've been developing OpenMP code, then you've probably been there. So the question is, where did my performance go? And the way I like to think about it is that it's disappeared into overheads of one sort or another. So I'd like to think about what types of overhead we can have. And so these are the 6.5 evils. So you can really think about overhead in OpenMP programs as falling into one of 6 main categories, which are sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention. And there's also an extra half, which is to do with compiler not optimizing properly, which I'll mention very briefly at the end. So what I want to do is to look through each of these and discuss what they are and how you can try and fix them. Okay, so the first one is very straightforward, which is sequential code. So in OpenMP, all the code that's outside parallel regions or is inside master or single directives is sequential code, and the time spent in sequential code will limit performance. So that's just a simple Amdahl's law argument. So for example, if 20% of my original sequential execution time is not parallelized with OpenMP, then I can never get more than 5 times speed up. So if that's the problem, well, that's easy. Okay, you just need to you haven't finished the job of parallelizing enough of the computational intensive part of the program, and you need to find ways of parallelizing some of the rest. Second evil is idle threads. So this is largely due to imbalanced load. So what typically happens is that some threads finish a piece of computation before others and have to wait for others to catch up. So very typically what you find is that you have threads sitting idle in a barrier at the end of a parallel loop or a parallel region. The way OpenMP is designed is that it encourages you to put lots of barriers in your code because there's implicit barriers at the end of every parallel loop and every parallel region. So this is just a pretty simple idea. So suppose I have 4 threads, and this diagram is supposed to show 4 threads, the activity on 4 threads, where blue is useful computation and red is time waiting. So if the third thread takes longer than the other 3 to reach the end of the parallel loop or the parallel region, then we get some overhead from the red parts, which are threads being idle. Again, nothing particularly complicated or sophisticated about that. So what can you do about load imbalance? Well, if it's a parallel loop, then OpenMP offers you a lot of opportunities to experiment with different schedule kinds and chunk sizes. So you can try static scheduling with a small chunk size, or dynamic scheduling, or guided scheduling. And there's a convenience. You can specify schedule runtime on a loop, and then you can set the schedule with an environment variable. So it just is a convenient way of running lots of experiments without recompiling your code. If you have very irregular computations, then, and particularly if you have irregularity or unbalanced loads in combination with nested parallelism, then using tasks can be helpful. It's designed, OpenMP is designed so that if you have tasks, then the runtime is supposed to take care of the load balancing for you. And in general, it does a reasonable job. You have to be aware that tasks also come with overheads, which we'll talk about later. But if load imbalance and messy, nested, highly irregular problems can certainly benefit from using tasks rather than the conventional loop constructs and or nested parallel regions in OpenMP. Just a word of warning that it's not always necessarily safe to assume that two threads doing the same number of computations will actually take the same time to execute them. Because what can happen is that the time taken to load or store the data may be different depending on if or where that data is cached. So so you can have what looks in your code like a perfectly well-balanced loop where every thread is doing exactly the same amount of computation, but some of you can have situations where some threads will take more cache misses than others, and that will result in load imbalance. There's other places where we can have idle threads, critical sections, another example. So in OpenMP, that would be critical regions or atomics potentially, or using lock routines to protect pieces of code. So this time the green stripy piece of activity is the contents of a critical region. So that can only be executed by one thread at a time. And so in this case, the first thread reaches the critical section first and goes ahead and executes. But all the other threads have to wait their turn through the critical region. So they also incur some idle time while they're waiting for access. What can you do about this? So clearly you can think about, well, can I minimize the time that's spent in the critical section and reduce the cost of the code that's in there? That will help. To OpenMP, critical regions are really just a global lock. Okay, they're really just a single mutex which gets locked on entry to the critical region and unlocked on exit. So you can use critical directives with different names. If you have more than one data structure that you need to protect, then you can use different names to protect them independently. If the type of critical code allows it, if it's just a simple update to a basic type, then use atomics if possible. That allows a lot more optimization. It allows the runtime to implement and runtime stroke compiler to do something better. Potentially use atomic instructions, or to construct a very lightweight critical section using compare and swap or similar atomic instructions. And it also allows things like, if you have atomics, then you can. It also allows the runtime to do. You can have concurrent updates to different array elements. So if the thing on the left-hand side of your atomic operation is an array element, if you use critical, then only one thread at a time can update any element. Whereas if you use atomic, then that allows the runtime the possibility to protect every array element separately. Or potentially you can do stuff with locks. You can, if you can't use atomics, then maybe if you have a lot of different data items that need protection separately, you can use multiple locks. So there are various ways to try and reduce the conflicts and the idle time associated with this type of construct. Okay, next evil is synchronization. So every time we synchronize threads, there's some overhead, even if the threads are never idle. Okay, because those threads have got to communicate somehow with each other that they've arrived at the end of the parallel region or wherever it is in the OpenMP code. And that's basically just done through the memory system. Okay, there's no special hardware to synchronize threads. It's all done through reads and writes to shared memory. So a lot of OpenMP implementations put a lot of effort into optimizing their barriers. For example, but nevertheless, it is just down to reads and writes. And again, just to emphasize, many OpenMP codes are full of implicit barriers, and they can be quite expensive. Obviously, it's how expensive depends on the number of threads you have running, which runtime, and on the hardware. But it can be on the order of thousands to tens of thousands of clock cycles. And then the other synchronization constructs, criticals, atomics, locks, they're not free either, and nor is, for example, creating or executing a task. How do you avoid this type of Well, this is really about granularity. So think about parallelizing the outermost level that you can, try to minimize the frequency of barriers. So that could potentially involve some reordering of loops and also therefore of array indices as well. But generally thinking about, can I get as much computation done between synchronization points as possible. So constructs like parallel loops have this barrier at the end by default. You can remove that by using a no wait clause on the loop directive. But be careful. It's obviously the default behavior is there to help stop you shooting yourself in the foot with race conditions, and you have to reason very carefully about when it's safe to remove barriers. Again, yes, atomics may, and in most implementations do have significantly less overhead than critical or locks. Technically speaking, that's down to the quality of implementation. There's no actual guarantee in the specification that atomics are faster, but in general they are. Okay, so that's synchronization. That's fairly straightforward. Next one is scheduling. So this is the overhead that's incurred where if we create computational tasks, but we're relying on the runtime to assign those to threads in some way, then we're going to incur some overheads because the runtime has some cost to doing that scheduling. Some of that may well be actually internal synchronization in the runtime. So some of that cost of scheduling is actually synchronization, which is hidden from you. So examples where this can be a problem is for non-static loop schedules and for tasks. If I have a piece of code that looks like this, so I have a loop with a very high iteration count, and maybe the loop body doesn't really do very much. It's fair, each individual iteration is pretty cheap. Then if I have a loop schedule which is dynamic and a chunk size of 1, so that means that every single loop iteration is shared out to threads on a first come first served basis, then that's probably not going to work out very well because the overhead of doing the scheduling and internally synchronizing between the threads to agree who gets the next loop iteration can be quite high. And if you're programming with OpenMP tasks, again, this is really about thinking about how getting the granularity of those tasks right. If your tasks are too big and you don't have enough of them, then that can result in load imbalance and therefore some idle thread overhead. If you've got too many really small tasks, then that can result in having these scheduling overheads. So the cost of the threads actually deciding when and where to execute those tasks can simply be too big. So yeah, with programming with tasks, you really have to think carefully about how do you control the granularity of the tasks and try to get that right. So the natural granularity that appears in your program may be too small. Okay, so there may be the algorithm that you're implementing may have there may be a very natural choice of what constitutes an independent task. But if that's too small and there are too many of them, then you're going to run into too many scheduling overheads. So you have to think about, well, how to group those natural tasks together into larger pieces of computation, and that's actually what you turn into OpenMP tasks. Okay, so far so good. Now we get on to the more difficult stuff. And the next evil is communication. And the problem here is that on shared memory systems, communication is kind of disguised. It shows up as increased memory access costs because it takes longer to access data that's in main memory or that's in another processor's cache than it does to get it from the local cache. And as talked about yesterday, memory accesses are expensive. It's order of hundreds of cycles for a main memory access compared to a handful of cycles for a floating point operation. And the communication between processes takes place via the cache coherency mechanism, which I briefly talked about yesterday. So this idea that the multiple caches have to be kept coherent to make sure that processors always read the most up-to-date value. So if one processor writes a value and then another one reads it, then there is some communication going on underneath to make sure that the first write has effectively to send a message to the other cache to say, don't use this data item anymore. And then when the second processor wants to access it, it looks in its own cache and says, aha, I have an invalid value here. And then it has to go to the remote cache where the value was last written to retrieve the latest value. And from the point of view of profiling or diagnosing this with tools, or just looking at your code and deciding where communication is happening, it's actually really difficult. Compared with message passing, the communication in shared memory programs is very fine-grained. It's on the level of individual loads and stores, and it's spread throughout the program. Now, if I look at my MPI program, I can very easily tell exactly where the communication is happening, because the only place it happens is inside MPI library calls. If I look at an OpenMP program and ask myself where communication is taking place, well, the answer is it's really hard to tell, because you can't very easily just eyeball a piece of code and decide which accesses are going to be cache hits and cache misses. And this fine-grainedness also makes it harder to instrument with tools. So tools can quite successfully instrument message passing programs and tell you exactly how much data was sent between which processors and when and how long it took and so on. But monitoring communication in shared memory is more difficult because of this very fine granularity that is happening there. Okay, so just to explain cache coherency on a single slide. Okay, this is highly simplified, and the real details are complicated, and the real details you can effectively not really find out because the cache coherency protocols tend to be commercially sensitive, and vendors don't release the full details of how they implement it. Essentially, you can, from the purposes of thinking about it from a programmer's point of view, a lot of the gory details are unnecessary to know about. So this is kind of very sort of top level view, but is enough to help us reason about performance of programs. Essentially, what's going on here is that if a thread writes a data item, it will get an exclusive copy of that data in its local cache. So exclusive means that is known to be the single up-to-date copy of that data item in the system. And at the same time, any copies of that data item in other caches get invalidated to avoid any reading of out-of-date values. And then any subsequent accesses to that data item by other threads have to go to where the exclusive copy is to get the up-to-date value. And this process takes time because that requires moving data from one cache to another cache. Okay, so that's very, very simplified concept of what's going on with cache coherency. But that's enough to give us a picture and to help us reason about what's going on in our programs. So what can we do about this? Well, this is really about trying to exploit data affinity. What do I mean by that? Well, obviously, the way caches work is that data will be cached on the processes which are accessing it. Okay? So just like sequential optimizations for memory, this is just really an extension of that. We have to try and reuse cache data as much as possible. So in a multi-threaded context, what that means is we need to write code with good data affinity to try to ensure that the same thread accesses the same subset of program data as much as possible. And also, it helps to make those subsets reasonably large, contiguous chunks of data as well. So not just individual words. I'll explain why that is in a minute. It's also important for the same reason to prevent threads migrating between cores while your code is running. Okay, so the operating system is prone to try to share, give equal share of hardware resources to all your threads, and it's possible, and that the threads can, as they're running, get migrated from one core to another. But if that happens, then it doesn't. The fact that the execution of the thread is migrated doesn't mean that its cached data comes with it. So if that thread carries on accessing the same data, that data has to come sort of bit by bit from the cache where that thread was originally executing. So there's various things you can do about that. In general, there's an environment variable in OpenMP, OMP proc bind. You can set that to true, and that says, okay, please bind my threads to processes and don't move them around. But batch systems will also do thread binding for you. For example, Slurm on Arch 2 is set up in such a way that it's integrated with the OpenMP runtimes, and you get thread binding by default. And of course, that depends on many things. Working depends on what batch system you're working with. Depends on how whether that batch system has been configured correctly. Depends whether the batch system and the OpenMP runtime actually interact nicely with each other. Although in principle we should be able to let the batch system take care of it, it doesn't necessarily work in all cases. Okay, so an example of data affinity and how it can go wrong. Okay, so a piece of code here I have are two sets of nested loops. So what I'd like you to do is to focus on the second loop first here, okay, and look at the array indices. So the data that we're concerned about here is this array A, okay, a two-dimensional array A. And the second loop reads values from A. Look at the loop indices. So the loop bounds are 0 to n for I, but 0 to I for j. So that means that if we want to parallelize the outer loop, then we need to take care of the load balance, because different I iterations do different numbers of J iterations. So we need to take care of the load balance. So you might do that, for example, by specifying a say for example a static schedule with a chunk size of 16, because that turns out to be the best schedule for this unbalanced loop. But now we have to think about, okay, if different threads are accessing different parts of this array A, where is that array currently cached? Well, that depends on essentially where it was last written. And it was last written in the first loop. So, but this loop has different indices, okay? So this is so I is still, loop bounds for I are still 0 to n, but the loop bounds for j are also 0 to n. So that means that's that's a balanced loop. We don't have to worry about any load imbalance. We can just use a plain old static schedule, which just divides the loop iterations up in blocks and gives one block to every thread. But we've now got ourselves in a situation where these two loops have different access patterns in terms of which threads are accessing which elements of this array A. And it turns out, if you think about it, that in the second loop, most of those accesses into A are by a different thread than wrote that element in the first loop. So most of those accesses in the second loop will actually result in cache misses. So in this case, it's there's a fairly obvious fix. We could obviously apply the same static 16 schedule to the first loop, and that probably doesn't incur much additional overhead in terms of the loop scheduling, but it makes the access patterns match up nicely, so that hopefully all the accesses in the second loop will be cache hits instead. So here's another example, perhaps a more common type of situation. So here I've got three loops. The first and the third loop are essentially identical, and so these the first and the third loops are parallelized, and they make reads to this array A. The loop in the middle is not parallelized, and it writes some new values into A. So what happens? So when we execute the first loop, then we will get copies of A spread across multiple caches. So different elements of array will get cached where each of the threads is executed. The second loop all executes on one thread, so that means that and they're write to A, so that means the of A will all be gathered into one cache where the master thread is executing. And then so that will incur some costs because those elements were originally there were copies in other caches, so the writes will be more expensive because of the invalidation process that has to happen at the same time. And then in the third loop, those reads of A will now, say, apart from thread 0, all those reads will now be cache misses again, because the exclusive copies are all where thread 0 is executing. So all the other threads have to get those copies of the elements of A from that remote cache. So patterns like this imply a lot of movement of data between caches. And as you can see, this is a fairly simple example, but it still requires quite a lot of thinking as to what's going to go on. And in general, with more complicated code, it's and especially if you don't know this necessarily, you have to also take into account the size of caches and also size of your arrays. It's really hard to figure out where this kind of problem is happening. So in this case, again, there's easy fix. It might turn out to be, well, actually, it's worth parallelizing that second loop, or even better, perhaps merge that second loop with either the one before or the one after. So what you'll see in this example is that, yeah, that's the sequential code will take longer with multiple threads than it does with one thread because of the additional invalidations. So that's quite non-intuitive. So what you will see is that if you measured the time for that middle loop when you're executing the code with one thread, okay, and then you measure it again executing it with multiple threads, you'll find that that middle loop, even though it's sequential, may take longer. Okay, so that's really not very intuitive. And you'll find that again, so the second parallel region is going to scale badly because of these additional cache misses. So it may turn out that you actually do need to parallelize code, which doesn't appear to take much time in the sequential program, but nevertheless, it's important in order to improve the data affinity. Okay, so far I've really just talked about cache effects. We also have to think about NUMA effects as well. Okay, so this is, if you like, doubly evil. So on multi-socket systems and systems like the AMD Rome that has these multiple NUMA regions on a chip, then the location of data in main memory is also important. And OpenMP has no direct support for controlling this. So there's no features in OpenMP that allow you to control the placement of data in main memory. So the common default policy, which is sort of baked into Linux, is for the OS is to place data, okay, on the processor, or in the NUMA region where the first access in the program to that data came from. So the first time that piece of data is written or possibly read, if you haven't initialized it, is that determines the location of that page of memory in the physical hardware. So this is so-called first touch policy. Now, for a lot of applications, that makes a lot of sense. Okay, so if I have a sequential application, so that this policy is clearly the right thing. Okay, so wherever that process happens to be running, then it gets its data allocated in the NUMA region where it's executing. Also makes perfect sense for MPI programs. So every MPI process has its own data. So every MPI process will get its data allocated in the NUMA region where the process is executing. Unfortunately for OpenMP programs, it can be pretty much the worst possible option. Because very often, if your data is initialized in the master thread, so you haven't parallelized your data initialization, and why would you? Because it probably takes a tiny insignificant fraction of the execution time, and then that's all going to get allocated on one socket or one NUMA region. And then the problem is that essentially having all the threads accessing data on the same socket or NUMA region becomes a bottleneck. Essentially, you're constrained by the bandwidth of a single NUMA region. And the additional latencies are also potentially a problem, but that tends to be less significant. And you do have slightly longer memory latencies to remote NUMA regions than to the local one. But the real problem is, in most cases, is actually contention for bandwidth. So what can you do about it? Well, it depends on the operating system. You may have some options to control this. So for example, in general, in Linux, you can use the NUMActl command to change the policy to round robin, for example. So that will basically just distribute your data pages cyclically across the NUMA regions. Alternatively, the first touch policy can be used to control data placement indirectly via parallelizing your data initialization. Okay. So even though that might not seem worthwhile at all in view of the insignificant time it takes in the sequential code, you might think, okay, in order to get the data distribution right, I will parallelize my data initialization and implicitly make use of the first touch policy to get it distributed across the NUMA regions. So typically, you don't necessarily have to get the distribution exactly right. In fact, in some applications, it's not necessarily at all obvious what the right or the most optimal distribution actually is. Depends on the access patterns to the data from the different threads. And so usually some distribution is usually much better than none at all. So it's really the first thing to think about is avoiding this pathological case where all the data is initialized on the master threads and all ends up in one NUMA region. So as long as you get some distribution, then that's usually makes a significant improvement. Of course, this depends a bit on the data structures in your code. If you're dealing with, if you have nice regular multi-dimensional arrays, then doing parallel initialization is usually pretty straightforward. If the data structures in your code are things that are organically grown, like trees or graphs, or things with lots of objects connected together with pointers in some way, then doing this can be much harder because parallelizing the data initialization may be much less. The other thing to be aware of is that what units is the allocation being done on. So it's being done on the operating system page basis. So it depends on the OS, but that's typically multiple kilobytes of data. And it's possibly if you're tempted to use large pages for other reasons, then you have to be slightly careful about that. So if you choose to use large pages where pages are then megabytes rather than kilobytes, then it may be harder to get, maybe harder to distribute data structures which are of the same size of as the, or order of the same size as the pages. And as if that wasn't bad enough, there's something that's even more evil. Well, it used to be. Actually, I think the balance has shifted somewhat in modern hardware. So fault sharing used to be really quite bad. Modern processors have some extra hardware and tricks in the coherence protocols to try and reduce the impact of this. But nevertheless, it's still worth knowing about. And I talked briefly about this yesterday, but the problem here is that the units of data on which the coherency operations are done is the cache blocks. So these are typically 64, 128 bytes, are always bigger than a single word, which is 4 or 8 bytes normally. Okay, thanks. Yeah, useful note from Michael there. So modern Linux kernels are starting to do automatic page migration to try and fix this to some extent. That's helpful. It doesn't always necessarily work. It depends on the access patterns and how rapidly whether the operating system can actually respond to it. Okay. Barbara says KMP Affinity scatters the same. No, it isn't. So KMP Affinity is controlling where the threads are executing, not where the data is placed. So so KMP Affinity is effectively the same as you can also do OMP proc bind. You can do the same thing in a portable way now. You can say OMP proc bind equals spread is the same idea as KMP Affinity is scatter. But that's controlling where your threads are placed, not where your data is going. Yeah. But that's interesting, Michael. I'd be interested to do some experiments to see whether the migration actually works. I did some work a very long time ago when this was kind of the same kind of idea was kicking around in SGI's operating systems. They implemented, so this is a long time ago, they implemented automatic page migration. And the answer then was it didn't really help very much. So it'd be interesting to see whether the Linux implementation can actually do any better. But yeah, as you say, it's probably it's if you can distribute the data up front, then it's better than relying on the OS to try and move it around for you. Good. So okay. So back to fault sharing, and the problem here is that what can happen is that if we have different threads that are writing to neighboring words in memory, can cache invalidations, because they are writing to the same cache, although they're not actually logically sharing any data. If they're writing to the same cache block, then that will kick the cache coherency mechanism in and still cause invalidations. So yeah, it's still a problem. Even if one thread's writing and the other's reading, that's still a problem. So if it's all reads, then it's no problem, because then there's no invalidation traffic. But if at least one thread is writing and others are reading, then we can run into this kind of problem. Okay, and so the worst cases where you have to sort of might ring alarm bells are where you have different threads repeatedly writing neighboring array elements. So you might be tempted to write some code that says, okay, I want to count some event or count something on a per thread basis. Okay, so have set up an array and then basically index it with the thread number, and then frequently increment the count for each thread as it goes along. So that's exactly the sort of thing that will cause this problem, because every write will invalidate the whole of the cache line, which other threads are accessing elements from. You can also get into the same sort of problems with just regular accesses in parallel loops as well. So the loop at the bottom here. So if you think about this one, so what's getting written here? That's elements of the array B, and so B's indexed by I, which is the parallel loop iterator in this case, and I've chosen a static schedule with a chunk size of 1. So that means that neighboring values of I are scheduled to different threads, and therefore neighboring values of B are being repeatedly written by different threads. So in this case, what you probably observe is, well, okay, so let's, can I choose choosing a larger chunk size will help. So if you did some experiments here, then you would probably find that for a larger chunk size, you'd avoid this problem. So you'll see that the performance goes down significantly as you make the chunk size really small. If you went from like 8 to 4 to 2 to 1, you could see a quite marked decrease in performance from this loop. So that's communication and data access costs, and that's all really quite difficult actually in practice. Not least because there's very little good tool support for diagnosing those kind of problems with shared memory. Last of the 6 is hardware resource contention. So the problem here is that essentially, the design of hardware is a compromise. But there are shared resources which all, of course, try to access at the same time, don't scale. Of course, you think of that the other way around, in the sense that an application that's running on a single core can access more than its fair share of the resources, and you might think, well, that's actually a good design decision, in the sense that these are general purpose processors. So sometimes they will be running single-threaded, single-process applications, and those will benefit in performance if there's nothing else running on the chip, then it's a good thing that process can get access to more than one core's worth of level 3 cache or memory bandwidth, for example. And it turns out this is, particularly with memory bandwidth, this is particularly noticeable on the AMD ROMs. So cores, and therefore the OpenMP threads that are running on them, will contend for memory bandwidth. They can also contend for cache capacity, and also potentially for the functional units if we're using hardware multi-threading. But memory bandwidth is often the big deal here. So codes which are very bandwidth hungry will not scale linearly on most shared memory hardware. And trying to deal with this is, in general, difficult. You really just have to think about trying to reduce the bandwidth demands by improving locality and reuse of data in caches. So obviously that's, that will also, it's essentially just the same as optimizing your sequential code for cache usage to try and reduce the memory bandwidth. But it becomes even more important in parallel codes because the available memory bandwidth is limited. Okay, so try not to throw too much sort of experimental data at you in these talks, because I think it can just be overwhelming. But I'm just going to show you one results of one experiment here. Okay, so on the AMD row. Okay? So I restricted myself here to just running inside one NUMA region. So just up to the 16 cores inside a single NUMA region. So there are no NUMA effects going on here. Okay. So just remind ourselves of the cache structure here. We've got level 1 and level 2 caches per core, and then we have 16 megabytes of shared L3 cache for every 4 cores, for every set of 4 cores. So what I did was just take this very simple parallel loop. So it basically just forms the sum of this array A. Okay, and okay, so originally I just compiled it up and ran it sequentially, and then run it in parallel using different numbers of threads, and then measure for different values of n, so different values of the size of the array, essentially measure the speed up that I got, okay, from this number of threads compared with the sequential version. So here we are. So what's in this plot is, on the vertical axis is the obtained speed up versus the sequential version of that code, and on the x-axis is essentially the value of n, the number of iterations. Okay, so what can we see from this graph? Well, can see that for small values of n, then we end up with a speed up which is much less than 1. So in other words, the parallel code is significantly slower than the sequential code. Okay? And that's just death by synchronization. That's simply the result of the overhead of synchronizing the threads at the end of the parallel region is too big compared with the amount of work. So it's quite interesting. You can see that it takes, it actually takes quite a lot. It takes, of the order of maybe something like 50,000 iterations in that loop before I overcome the overheads of the synchronization. So anything less than n equals 50,000 is you're just onto a loser, because the overhead of parallelization is too big. Okay, so the pale blue line here is 2 threads. So what you can see is that it behaves pretty much like you expected. Once you overcome this overhead of synchronization, the speed up settles down to around about a factor of 2. Okay, so for large enough value of n, then I get pretty much ideal speed up threads. Then as I go to 4 threads, so that's the orange line, it gets a little bit more complicated. So the speed up initially goes up to about 4, but then it drops down to a little over 3 for a while, and then eventually it drops back down to something that's only just over 2. So what's going on there? Well, for when it drops down to about 3, that's where the data is the data doesn't fit in level 2 caches anymore. And what we're seeing there is contention for the level 3 cache bandwidth. Okay, so we've got 4 threads. So we're using all the cores that are connected to one of the level 3 caches in this case. So we are actually saturating the bandwidth to the level 3 cache. Then for 8 and 16 threads, we also see an increase, and then we see this big spike. So what's happening with 8 and 16 threads is that eventually, for large enough values of n, we are getting that data spread across multiple level 3 caches. So we actually get some superlinear speed up some cases because there are data sizes where that array did not fit in one level 3 cache, but if we distribute it across 2 or 4 level 3 caches, then it does fit. But in every case, once the arrays get big enough right towards the right-hand end here, we drop right back down to a speed up which barely reaches about 2.5. And this is where we're no longer running in cache. We're running basically out of cache into main memory, and we're contending for memory bandwidth. So you can see here that on the AMD ROMs, it's really quite severe in the sense that just two threads, so running on 2 out of those 16 cores in a NUMA region, are able to consume almost all of the memory bandwidth, and that adding more threads, you don't get very much more bandwidth at all, and therefore you don't get very much more performance. Okay. Now, Mike asks, does how you set up make a difference? Oh, I'm not sure quite what you're asking there. Is that down to the simplicity of the loop? Well, it's down. The simplicity of the loop means that the entire cost of this loop is effectively in memory accesses. Okay, so the floating point computation is absolutely irrelevant. Okay, does the distribution of the data in A? Well, the distribution of the data doesn't make any difference here because I'm all in a single NUMA region. Okay, and basically what I'm doing is actually I'm repeating this calculation many times, so that I'm repeating this loop lots of times so that everything settles down to where it belongs. It's going to be. So basically, I'm basically ignoring the any first time through effects which would come from where you initialize that, where that data was originally in the caches. Yeah, sorry, should have said that. Yeah, so it's basically repeating this loop enough times so that any first time through effects are basically washed out completely, and what you're seeing is the long term behavior once everything's settled down to where it's going to live in the caches. Yeah, so for a loop like this, yeah, so you have to realize that, you know, as n increases, then the floating point operations here become increasingly less relevant for performance. It really doesn't matter anymore. You know, think that you're, you know, because this loop vectorizes very nicely, so you get you know, you get what is it? Get 8. It depends on the type of A, but you get 8. You get, you know, eight floating point operations per clock cycle, potentially out of this. But every 8 words will be, you know, once it's big enough, once A is big enough and doesn't fit in level 3 cache anymore, every 8 iterations will be a full main memory access, which is several hundred clock cycles. Yeah, absolutely. So yeah, that's the roofline model would basically reveal the fact that this, you know, for large N, this is essentially bound by memory bandwidth rather than by the floating point. So roofline models are okay, but the problem is that it's always a bit tricky as to which roofline you're working to. Okay? It depends on, you know, whether you're, it depends on the size of your data, whether you're single precision or double precision. Depends on whether you're vectorized or not. Depends on which level of cache you're getting to. It's a bit of a case of summation. Yes, okay. So the reduction just reduction gives every thread its local copy of sum, which it accumulates into, and then they're added up together at the end. So really, the only reason for doing this was to keep this keep the code really simple, so that it's just doing reads. And, I mean, you would, if you did a vector copy or something, you would see something very simple, very similar as well. But yeah, so the in terms of the data access, the reduction here doesn't matter, because that's just at the end of the parallel loop, everything gets summed up. So for small values of n, that reduction does contribute somewhat to the cost of the end of the parallel region. For large values of n, it's completely insignificant. Yeah, it was just really that I wanted something that was easy to reason about, in terms of, okay, it's only reading data and not writing it. Okay, so what else? Yeah, so other potential contentions, systems where cores share some level of cache, then, you know, again, you may see this apparent lack of scalability, because a single core can access the whole of the shared cache. So one potential problem here is that if you are doing cache blocking optimizations in your code, then you may need to beware of tuning your block sizes for a single thread and then running multi-thread code, because the way you've tuned it, each thread is going to try to utilize the whole cache, which it then will not have access to, because of the other threads contending for the cache space. I said something about hardware threads yesterday. So it's also potential that if you're threads running on the same core using hardware thread support will contend for functional units as well as the cache space and memory bandwidth. So hardware threads tend to benefit codes where threads are idle because they're waiting on memory references. And that's typically codes with non-contiguous or I'd say random, but poorly structured memory access patterns. So codes which take a lot of cache misses can benefit from hardware threads, because while one thread is stalled waiting for memory accesses, then the other thread can make progress. And codes which are bandwidth hungry or which saturate the floating point units, things like dense linear algebra, may not benefit from hardware threads, and you may actually find that the code runs slower. So which, as I mentioned yesterday, is why that they are often disabled by default on a lot of systems. Okay, so obviously the other way you can get contention is by oversubscribing. So running more threads than you have hardware execution units, be that physical cores or hardware threads, is generally a bad idea, because then the operating system has to try and give each thread a fair share, and the cost of context switching, so stopping one thread and starting another, is pretty high, and that also tends to it also ruins your data locality, because whenever you switch a new thread in, then the cache is full of the data that the previous thread was using, and that also contributes to why this is in general a pretty terrible idea. Okay, so that's the sixth. I promised you a sixth and a half, and this is rare, but it's just worth knowing that it can happen. And this is compiler non-optimization. So in very rare cases, adding OpenMP directives can actually inhibit the compiler from performing some of its sequential optimizations. And the symptoms that you will see here is that if you run the parallel code on one thread, then you get a longer execution time than the sequential code without any OpenMP directives. So thankfully, this is very rare. If it does happen, it can be very hard to find a workaround. It can be very difficult to figure out how the optimizations are conflicting with the directives. Sometimes you can cure this by essentially telling the compiler more about variables, or making the compiler make less worst case assumptions. So if you can, making private copies of shared data where that's possible, or making local copies of variables in routines, can use a local copy, and so even to the extent of start the routine, copy something into a local variable, use that in the parallel region, copy it back into the global variable at the end. So even tricks like that can sometimes help. But thankfully this is rare, but it's just worth being aware that if you're very unlucky, it might bite you once in a very long time. Okay, so let's just back off a little bit and think about sort of broader strategic things here. Okay, so how do I go about minimizing overheads? So I'm in this situation where my OpenMP code is giving poor speed up, and I don't know why. So, well, what do I do now? Well, a hope that can convince you not to say OpenMP is just a heap of rubbish and give up. Strategy that I think is helpful here is to try to classify and localize the sources of overhead. Okay, so which one of those 6 problems is hurting you, and where in the code is it happening? So if you can figure that out, then you have a fighting chance of targeting code optimizations to make progress in performance. So basically, yeah, what type of problem is it? Where's it happening? And obviously, it's helpful to use available tools to help you. Timers, hardware counters, profiling tools can obviously try to help you to nail some of those things down. And then obviously, as with any profiling, yeah, okay. And fix problems which are responsible for large overheads first, and then iterate. Mark says, yeah, the other challenge, people commenting, why expend the person effort? Use all the cores for MPI. Yeah, for quite a few applications, that's pure MPI is still making sense. But I would say we are increasingly seeing the use of hybrid MPI and OpenMP codes on large systems. It's not a magic fix. It takes quite a lot of effort and thinking. So I'm not going to cover some of the issues of hybrid programming in this course. So in terms of profilers, it's a bit tricky with parallel code, with shared memory code. Your standard profilers, so things like gprof or what you get in your favorite IDE, can be pretty confusing because what they do is they just typically accumulate the time spent in functions across all threads. So they basically don't show you, you can't tell if some threads are spending longer in a given function than others from basic profiling. You can get a lot out of using timers, so you can use OpenMP's built-in timer routine if you choose. So what I would often do is add timers around every parallel region and also around the whole code, or at least the whole code that's performed, the whole piece of code that's performance critical. So this at least allows you to do the localization bit. So that means that you can compute speed up. You can compute your speed up on a per parallel region basis, and that tells you a lot. Okay, it tells you which parallel regions have the big problems. And again, so you can also say, okay, if I know implicitly, if I know the time for every parallel region, I know the time for the whole code, then I can subtract and work out how much time was spent in sequential code as well. And yeah, so don't necessarily assume that doesn't change with the number of threads. There's various tools out there that can help you. So yeah, when Cray, obviously Cray does some stuff. I quite like, it's down to personal preference. For OpenMP hybrid codes, I quite like Scholastic's way of breaking down overheads into different categories in the manner that I've done them. But the main problem with these tools is that pretty much none of these tools will tell you anything about communication overheads or hardware overheads. They're quite good in synchronization overheads and load and balance, but the communication and hardware and things like bandwidth contention, no. Okay, it's very difficult to get that out of tools. One I know that does do something very different and that does help you with that kind of thing is Thread Spotter. It's at least I think that's still its current name. It works very differently. It basically takes a statistical memory trace and replays it through a cache simulator. So that does allow it to look for these kind of cache and memory problems, which the other tools simply can't tell you anything about. Okay, yeah, and there's so there's a practical associated with this. Okay. So you can try optimizing a piece of. There's an opportunity to try and optimize a piece of OpenMP code if you want to. Okay, good. So that also went on a bit long, but hope that was useful. Anybody, any more questions? Okay, so I thought I'd just finish up this session by having a quick look at the OpenMP optimization exercise. So see what you can see with CrayPat on this one. It's kind of okay, but if you like. So I run the code as supplied on the 16 threads. I get a runtime of something just a little under 4 seconds. And essentially the profile tells me that, under user time, I have, it tells me it's spending time in forces loop at line 24. When you build stuff with OpenMP, when you compile and profile with OpenMP, it basically tells you where the construct came from. Essentially, because it's the compiler's generating a separate function that comprises the loop body. So it tells you that it's a parallel. It basically tells you it's a parallel loop at line 24 in forces. So it spent 72% of the execution time in there, but the imbalance is quite high. It reckons there's about more than 50% imbalance in there. So basically, that means that some threads took twice as long as average, roughly, to execute in there. And then you can also see, so underneath in the OMP group, it says, okay, 24% in OMP set lock. And this is a bit confusing because the code doesn't directly call OMP set lock, but so you kind of have to figure out what this means for yourself. So what's actually going on here is that inside the runtime library, the critical sections in the code are being implemented using OMP set lock. And that's actually what the profiler reports as where the time's coming from. So that is okay, but not tremendously helpful. And again, there's also a little bit of time in spin weight under the ETC group, and that's also confusing. That is almost certainly coming from the barrier at the end of the parallel region, but that doesn't even attribute that to the it's because it's spending its time actually in basically in a system function, which is probably called by the barrier routine inside the OpenMP library. It actually doesn't attribute it to OpenMP here. So that's probably actually the time spent waiting in the barrier at the end of the parallel region, but that's kind of not very obvious. That's somewhat obscure, but it does tell me that there are probably two performance problems here, two sources of overhead. One of them is idle threads because of the load imbalance in the loop, and the other one is idle threads because of waiting for entry to the critical section. So okay. I look at the code, so I can fix both those problems. Essentially, I can fix the load balance by changing the loop schedule from static to static 1. So that's just a simple interleaved schedule. And then by replacing the criticals with a bunch of atomic updates to the elements of F. So where does that get me? That gets me down from 3.9 seconds to about 1.8. So that improves the performance quite a lot. And profile now tells me that I'm now spending 93% of my time in that forces loop, but the imbalance is now down to, there's only 1% imbalance instead of 50-something%. And one of the other user routines, make ekin, starts to make an appearance, but there's still a bit of time in spin wait. So again, that's still the barrier at the end of the parallel region, which is causing that. Okay. Any questions on that? Please let us know. Otherwise, we'll take our lunch break now and resume with Adrian talking about vectorization and memory optimization at 1:30.